Anyway, so this is like I said, it's going to be my first time doing XC comparison to XE and early performance tips, and I'll admit it's not really a smooth running thing of like I talk on one topic for 45 minutes. It's going to be a couple of slides. We'll see where we go with it. So the basic outline is the node is similar, very similar, except for completely different. And you're seeing some of it, right, already. Choice of hyperthreading is new. Intel OpenMP on the XC. You just got some of that already. I'll give you my version of it. Environment is very similar. I told you that already, and really I do believe that to be true. Many of the things are extremely similar. The biggest change is Intel. There's a couple of MPI enhancements, and at least one of those enhancements was already on Hopper, but not nearly so useful. I go through a hyperthreading optimization chart, and this is kind of like how I would maybe approach it, if you will. Network bandwidth, I again reiterate that. Brush up on your I/O. Might get in trouble there. But then if we have time, I'll tell you a story about 3D FFTs. And the 3D FFT story is applicable to both Hopper and Edison. So it's not necessary that we go over it, but if there's interest in 3D FFTs, then we can talk about it. So this is a picture of the Magni cores on Hopper, a Magni cores node. And I put this up so everyone remembers what it actually looks like, right? So we have the interconnect, starting from the interconnect. We have the interconnect, it's connected through HT3 to the Gemini. That interconnect connects to one of the sockets, okay? But what's inside that socket are actually two different die. So even though physically it looks like there's two sockets on there, and yes, the definition of our terms are becoming overloaded and confusing, and we have to write contracts about this stuff, so it drives us batty. But you have two sockets, but really inside that socket are two different die. And I don't know if you're aware of this. Most people, they just start to think about there's 24 cores on a node, and that's the way they think. Maybe that's not the way they think, but that's the way it is. So, but keep in mind this: there's two sockets, one of which is attached to the network, and then you have cores inside those sockets. And actually, in the case of Magni cores, you have two separate dies inside the sockets. Now we're going to move to the Intel. Okay, so at a high level, it's very similar. It's very similar in that I have two sockets. Each socket has a direct attached memory. There's a connection between the two sockets, and one of the sockets is connected to the Aries. So from that perspective, it's very similar. But if I add my own little sub-block diagram, what's very different is that what is inside that socket is now a single die with 8 physical cores on it. Okay, so I don't have this 2 die thing, and I don't have 12 CPUs inside of a socket. I have 8. All right, so we have to keep in mind, okay, very similar, but yet the number of cores and their definition are changing. So now I'm going to go to, I think, a very dense slide. And it's my Magni cores versus Sandy Bridge bake-off. And I know there's a lot of things here. And ideally, you'll have this slide, and then you can just keep on referring to it. Oh, what was this? What was this? Right? But so let's just go down, and every single line should be, I should have the same information on both, on every line. Left-hand side is Magni cores, right-hand side is Sandy Bridge. Left-hand side, 6 cores per die, 4 dies per node. Sandy Bridge, 8 cores per die, 2 die per node, all right? Each core has On left-hand side, 1 user thread. Right-hand side, 1 or 2 user threads, depending on what you put on the app run line, or depending actually, since default is 1, depending on if you put anything on the app run line. So left-hand side, 1 SSE vector unit. Right-hand side, 1 SSE vector unit. They're both vector machines down at the core, and really, to get maximum performance, you want clean stride 1 vector code. That's about all I'll say about that at the moment. But the left-hand side was 128 bits, and the right-hand side is 256 bits. In 64-bit words, that's 2 words and 4 words. So they double the vector length on the right-hand side. And then 1 add multiply, 1 add multiply. That's what's in the functional unit, but since it's twice as wide, that gets to double the peak per clock, is what the right-hand side does. Okay? Now we're going to get into caches, and this is going to be interesting. We're still under the core basis, right? So the left-hand side has a cache size of 32 kbytes, right-hand side 32 kbytes. They're very similar there as well. Left-hand side, 0.5 megabyte. Right-hand side, 1/4 megabyte. So actually, the Magny-Course has a larger L2 cache than Sandy Bridge. I mean, if you're getting really into cache blocking, this is going to be, kind of what you need to look at. But this is going to be interesting. The L3 cache size is 6 megabytes on the Magny-Course. 6 megabytes, and remember, the L3 lives on a die. On the right-hand side, the L3 is 20 megabytes. So this is 6 megabytes shared. Well, you'll see cache per core. 6 megabytes shared by 6 cores. I end up with 1.5 megabytes per core, if you want to think of it like that. And this one, I've got 20 shared by 8, which is 2.5. Now here, actually, I'm ignoring how they do their cache coherency and if it's inclusive versus exclusive. I won't even go there. And I can't quite keep straight myself. But so the cache structure is changing because where I say, the cache size is tripling. Well, it's tripling divided by 2 because there's twice as many die over here. So if you really get into how your job is placed and how many things you're using, you're going to be able to use this this slide, hopefully, to at least answer some first round of questions. Okay?
So I have one observation that it looks like if we say that small benchmarks, kernel benchmarks are showing a factor of 2 over Hopper, is that the 256 versus 128 that we're primarily seeing there? 8 results per clock?
No, you're seeing everything on this slide and more.
Okay.
It's a combination, and it's not an easy choice. So basically, a question: when I'm running 2 times faster, one thing you're going to have to ask is 2 times faster than what on what basis?
Sure, I know.
Right? And if you're on a per CPU basis and you've loaded it up, remember that if you are just in default mode, you actually have fewer ranks on a particular node. So fewer ranks sharing roughly the same amount of bandwidth, having different caching, everything has changed underneath you. So it's interesting when you just move over a code and you're running in default, you can see a really big boost in the per CPU number, speed, a big boost in speed on a per CPU number. But if you guys are all charged on a per node basis, be more careful about what just happened, right? Yes.
So this is a question really about changes, because obviously phase 2 is going to have, quote, a processor to be announced, close quote, something like that. So can you hint at what might be constant and what might be changing on this? Are there some takeaways that may apply for the future?
Nick? Or someone?
I'll probably get in less trouble answering this than he will. I think. Well, okay. So let's do this experiment, which is much safer. If you look at the difference between the Halo and the next one, which was called Westmere, basically that was the same thing.
It
was a die shrink with the same technology. right? So what the die shrink enables you to do is to put more cores per unit real area, and those cores are basically the same, right? So all of the information that's closely tied to the cores probably going to stay about the same. The memory bandwidth number will not increase quite as rapidly as the number of cores. That
And I hope people on the phone heard Nick because I can't repeat it. I have to be careful. So, okay.
So let me ask a question. So does this mean then for a socket, make sure I speak everything properly, we no longer have to worry about these kind of 4 separate memory domains within a
Within
socket? that we-
Two separate memory domains within a socket. 4 separate memory domains within a node
on Hopper.
on Hopper.
on Hopper.
Right.
Right. But now we just have
Two per node.
two. One per socket. Everything on a socket is equivalent, right?
Yeah.
Everything on the socket has equal access to everything else on the socket, as long as you're not talking about the L1 and L2 cache. They have equal access to the L3 cache and equal access to the memory bandwidth. Yes.
The other thing I think that's true that's not on here is that there's links between the NUMA domains are faster on the Sandy Bridge than the main cores, but I can't remember by how much.
They are, someone was asking me about the links well, so it's interesting because on MagniCores, the links between the die actually have a topology to
Yeah.
them because there's 4 and not 2. And now we're down to 2, so, it's a direct connection. So remember, the topology changed and then the speed changed. And I've actually tried to look at this, and people ask, what's the all-to-all bandwidth? What's the all-to-all running on? It's actually harder than I thought it would be to measure the bandwidth between the 2 sockets. I do know that according to the hardware specs, that bandwidth is way higher than like the PCI bandwidth to the network or something like that. But trying to write a test and see what it is harder than you think because you've got cache coherency going across that thing as well, and things are moving 2 or 3 times when you think you're only moving 1. But the bandwidth between the 2 sockets is pretty good. But I wouldn't test that. Don't get-
When will it be known what the new chip for phase 2? When can we put up a similar slide for phase 2?
We're thinking early July, I guess.
Well, that's when it becomes available. When will we know?
We'll know when it arrives, for sure.
No, so, okay, I mean,
that
look,
reassuring?
if you Google Intel processors, right, Ivy Bridge is the one after Sandy Bridge. Nobody is revealing anything secret there, right?
Just Google these numbers for Ivy Bridge and then you'll have to know.
No, so let me, so just finishing the thought, you can draw analogies between the Nehalem to Westmere upgrade to give you some idea of what will happen. But that won't give you every idea of what will happen. And the next sentence I was going to say, I'm not going to because it's still a deal. But the key question is always how many cores is going to go up to, and that's where we get into difficulties. And that's kind of why that next column doesn't exist. Most of the other numbers, you can, with knowledge of basic industry trends, you can figure out. The cores is a different.
So let me continue down my little line. So I think we were about a cache size, right? So the cache size is increasing massively on a per die basis, but don't think that you're getting 3 times as much cache because the number of dies is shrinking. So you just have to be careful if you're going down to this detail in the first place, right? I don't know how many people go down here. But the next 2 lines are, I think, very telling, very surprising, and I've asked to recheck these, but this is what I'm told, okay? So I'll just repeat what I'm told. Cache bandwidth per core. Now I remember where's a core, how many cores, where it's going. But L1, L2, L3 on Magni cores was 35, 3.2, and 3.2 gigabytes a second per core. And I think this is all cores firing simultaneously, right? On Sandy Bridge, it is 105, 42, 26. There's no dots in there, right?
Yeah.
It's an enormous difference. Enormous difference. And I know Intel, that's one of the advantages of going to Sandy Bridge, is the cache bandwidth is much higher. And this is now how many year old chip. I mean, we expect things to get better. But so one of the things I think we're finding is if you're running much faster on Sandy Bridge, there's a good chance that it has something to do with this. Probably more than the fact that the vector length doubled, right?
Right, so what we've seen is from 2 to 3x speed up per core. The more you are in cache, the closer you'll be to speed.
Okay, so Nick, in case you didn't hear that, what they're seeing when you're running what I will call single stream mode with one user thread per physical core, they're seeing 2 to 3x, and it tends to be that the number of that you're closer to 3 if your application is more cache friendly. Is that what you just said? More or less.
Is there any relevant latency number between L1, L2, and L3?
I don't have it. I don't know. Do I have a latency? No, I have a memory latency down here.
Yeah.
I don't know the answer to that. Latency at that low a level also becomes. I love the Heisenberg uncertainty principle. It explains so much about supercomputing, really, because the more precisely you want to know about something, that the speed it's running, the greater the chance that looking for that information will slow you down, right, or affect your speed. It's true about latency. It's true about barriers in an MPI application. Remove barriers, you're probably going to go faster. You might get the wrong answer once in a while, but you'll probably go faster. So, nonetheless, so I don't have latency to cache numbers. So the stream triad bandwidth numbers, if you remember on the previous presentation, I was comparing to Interlagos, okay, and those were much closer. But if we look at the stream triad bandwidth per node basis, we're going to from 52 to 77. So we're getting a nice boost. It's not a 2x boost, right? It's not even close to a 2x boost. But you can see where Nick is coming from. Then you can see 2x improvements while the number of cores is going down a little bit. So that kind of helps my number. But if I'm in cache more, then I'm going to be affected more by the characteristics on the line above it. I should have these lines numbered. On the line above it rather than the bandwidth number. If I'm just a streams number, then then you can probably, if my application is completely dominated by memory bandwidth, you can probably figure out your speed up today without even trying. But you'd be surprised. So clock speed on Magni cores, well, this isn't just Magni cores. I think this is the Hopper number. It was 2.1. I hope I got that right. And on Edison, it's 2.6. Now, this was meaningful. This is less meaningful. Meaning, Sandy Bridge is less meaningful because it's bouncing around on you. Okay? And we spend considerable effort to make sure it always bounces up and never bounces down. And hopefully we get that right. But it's still bouncing around on you.
Now, when you say that, are you referring to turbo mode, or is this something other than what is normally called turbo mode?
So the short answer is yes, and I could just leave it at that. I think the longer answer is that they keep on redefining turbo mode and what it is, because there's also the power saving mode,
Okay.
right? That takes it down. And really the definition of turbo mode has changed. So, but yes.
Okay.
That's it.
So actually, I haven't observed this on Edison, but we have a Sandy Bridge cluster, and on that one, when turbo mode is on, the frequency can go up to 3.0 gigahertz. So that's what we see, but it never went down to, it should like 2.6 or something like that.
Yeah, that's yeah, and actually, I think if you get really into it, the upper number is tunable, and there are pros and cons to making. I think if you can make an upper number higher and higher, but then you'll spend less and less time there. So, and I mean, hey, I think we've had people spend hours on the phone trying to figure this out, and it seems like we. Okay, we've been trying to figure this out, asking people that should know, and it doesn't always seem like. Right.
Well, the problem is it's related to heat, right? The faster the clock, the hotter it gets. So
on some chips, it's rated to heat. Some chips is rated to heat. Others temperature. Others, another one is power. Another one is clock. So you get really down into, you like have to find the engineer that designed it
right.
to know. So.
And then you get an answer of maybe.
So another one is this one is similar to what we just talked about. Peak double precision floating point per clock is going from 4 to 8. So the peak is jumping on a per clock basis. And so the peak double precision floating point per node is then I take this, multiply by the number of cores, and multiply by the clock speed. We're going from 200 to 330 about is what's happening on a per node basis. Now memory latency is improving, which means going down from 110 down to 82. But again, some codes will see it. Who knows if you'll really know if you're seeing this as opposed to something else. But this is a nice little slide. I've done a few versions of these with a bake-off, but this will help you to kind of know what's happening to you, and you can guess as to which one of these lines is the most important line to you. But
I think that the peak float count per node, the unit is the flop per second, not the flop per clock.
oh, you're right. Yeah, that's a flop per second.
So I was curious.
Yeah,
Oh, yeah.
yeah, that's a typo. So the peak double precision floating point node should be flop per second. That's a typo.
And I guess it's worth saying in both cases, actually I hope this is true now I'm going to say it, is that single precision is still twice as fast as...
In both cases,
cases.
the peak single precision is twice as fast. I have not done tests to... Wait, is that true? That's true on Magni cores, right? I think so. Yeah. So I have not done tests to see how effective they are at those, comparing the effectiveness on either. But peak is double, yes. Okay. So single stream versus dual stream. Everyone calls this hyperthreading. We had to come up with a terminology because really, if you look at Interlagos, if you look at Intel, the two chips are very similar, but they're talked about completely different, right? So, and hyperthreading is a proprietary term. So we are trying to come up with a way of describing what's going on. And really, the point is that unlike my understanding of how most Intel clusters are out there, keep in mind I'm inside of Cray, so I don't get much access to Intel clusters are out there. But the way I understand it, almost everyone boots and configures their Intel clusters to have hyperthreading off. It's just simpler, and MPI run and everything works better. And so probably the way I gather is that if you're running on an Intel cluster, you're probably running with one user thread per physical core. And that's why also everyone says, well, cores are well defined. Well, it was well defined because this was shut off. Cray was looking at this, and basically it was decided pretty early on that there's no reason to shut them off. It's an additional capability that you can choose to use, and we can give that choice not on a boot time basis, not on a reservation basis, but on a runtime basis on an app run line. And so what we have ended up with is we added an option to app run. J1 is single stream mode, which is 1 rank per core. If this is just MPI, single, no threading, right? I'll use the term rank, right? Or -J2 is dual stream mode, which is 2 ranks per physical core. Or you might say 2 ranks, and then there's 2 virtual cores on the 1 physical core. Or you might say 2 ranks per compute unit. Choose your terminology here.
Should I think of this as similar to the Blue Gene Q, where you have, I believe, 16 cores, but can have up to 64 threads?
So obviously I've never logged into a Blue Gene Q, but I think the answer is yes.
The answer is yes, okay.
It's actually, well, okay, I mean, yeah, the difference on a Blue Gene Q though is each chip, each core can do 1 instruction per thread per cycle, and 2 instructions total per cycle. So you have to use at least 2 threads on the Blue Gene to even saturate the instruction stream. On an x86 like this, you don't. 1 thread will saturate the instruction stream.
Right.
So, in a sense, that's worse or better depending on your perspective than this is. So there is a difference.
Yeah.
Okay.
Yeah, and so Intel calls it hyper-threading. IBM has called it symmetric multi-threading, at least at one point.
At one point, the
Yes.
power ones were called that, right?
Yeah, so there's been a few different names, but they're all basically trying to say I've got more than 1 PC process counter on a physical core, and the hardware engineer is going to try and choose which instructions to issue when. And some are better at doing that than others, even within the same organization, right? Because Intel, I think, if you go back to the Nehalem days, no one tried to use this.
Well, right, everybody tried it.
It was and by the way, I think you owe me something because we almost got a bet as to whether or not it would be beneficial on Sandy Bridge.
I lost that bet. That's true.
And the last line tells that story. But anyway, the default is single stream. So if you don't say anything, I'm repeating what Zhenji told you, but I'm saying it in a different way, which is probably good to hear something a couple of different ways, right? So the default is single stream, so you don't have to put J2. You can, but you don't have to. And when you don't put anything,
J1.
J1. Sorry. The default is J1, so you don't have to put anything. You can put J1, and it will behave the same as a default. But if you don't put anything, that's the behavior. J2 is the dual stream, and you can put J2 on there. And then it's gonna magically say, oh, well, now I am going to use those hyperthreads, those virtual CPUs on the physical core, and I'm gonna load up the process
But
like
that
that.
will only work correctly if you have that MPPPN in your PBS.
Yes.
Yeah, exactly.
Well, I would say it only makes sense because correct by, I mean, this is, it, to me, it only makes sense if you do that. I will point out, though, that if you do MPPN equals 32, that doesn't mean that you have to run with J2. You can run with J1, right? So the dual stream, this is high-level fuzziness, right? But the dual stream, well, if throughput is more important, or if performance per node is more important, or if your code scales extremely well, dual stream might be a good idea, right? Because you're in this case, your optimization function is not necessarily performance per CPU. It's not even necessarily maximum performance. It is the amount of performance for the resource that I'm using.
Efficiency.
Yes. And if you are charged on a per node basis, this might make sense. I say might, because it's not always true. And the obvious counterexample to all three of these points is HPL. Okay, HPL, throughput matters. It's the peak flop of the machine that matters more than anything. Performance per node, it's another way of saying the same thing. And HPL is believed to scale extremely well, and yet HPL gets its best performance in single stream mode. So this is not an absolute by all means, but nonetheless, single stream mode often is better. Well, if single job performance matters more, if performance per core matters more, and when it matters often more is the code doesn't scale very well, right? And that's why a lot of these ISV guys, they care about this one. This is all they care about, is because their codes are scaling to 256 nodes, and the users of ISV codes are charged on a per CPU hour basis, not on a per node basis. Then this matters more. So there is no right choice. It's just which one you want to choose. And this is my bet with Nick, which I'll keep on bringing up because it really feels good, is that in the end, there's this concept of SSP codes that goes into the contract. You don't need to know much more about it, but according to the optimization function, we ended up running 4 of the 7 SSP codes in dual stream mode. And I'm not going to say that half of all of you guys are going to end up running with dual stream. I think it will. I don't know what it will be. It could be less than 50% pretty easily, but I do believe it will be more than like one of you. It will be, there will be some multiple number of you that will find benefit in using dual stream mode.
So I have kind of a naive question, and you've shifted the terminology here from threads to streams, and maybe this is part of the reason why. I've always historically thought of, threads and processes as different things. And in the MPI world, you're talking about heavyweight processes. And then here comes this term hyper-threading, suggesting that full MPI processes per CPU, per virtual whatever, is not the way to go. But it seems like every time we get back to this concept here, we're still talking about running twice as many MPI processes as there are physical cores. Now, is a threading model appropriate for hyper-threading? Or am I
let me go back to your very first half of the sentence.
Okay.
And maybe that will help form the rest of the thing. The reason why I am using the term stream here is because threading has become overloaded. Threading, Intel says hyper-threading, and OpenMP threads, MP threads, right? And we're not talking about threading here. We're not talking about OpenMP threads running on hyper-threads. We're not limiting ourselves to this. This is 2 instruction streams. But yes, when we talk about dual stream mode, if you have a pure MPI application, you are talking about running 2 MPI ranks per physical core. I got them. 2 rules.
2 rules.
Try it.
Yes, exactly.
Take the one that's faster.
Exactly.
That's what you do.
And I think the third one is that letting us know what you found out when you tried it, so we can try and build up the knowledge.
But yeah, and one more comment about the OpenMP thing. This was actually relevant for Interlagos. But remember, I said Interlagos is actually extremely different. Extremely similar. They just talk about it different. Well, there was some indication that when you do OpenMP, if your OpenMP is at a relatively high level and the working set size is larger than the L1 and L2, well then it's behaves the same as 2 MPI tests. 2 MPI tests, 2 OpenMP tests, it doesn't matter. They're both thrashing, they're both competing for those low level per core resources, if you go back a couple of slides. So it doesn't matter if it's an OpenMP or an MPI code. But OpenMP does provide the opportunity, should you choose to try and use it, of if OpenMP happens to reuse low-level data, a small working set, and that suddenly, you get to use 2 threads and yet one L1 and L2 cache, maybe there's some benefit there. Maybe.